Hey everyone, welcome back to this course of Digital Electronics made easy. This is your educator Jayant. Let's get started. Okay, so in the last class we started designing these digital circuits, right? So now many of you, I don't know if you have got this question or not, but how fast can the circuit work? That should be a question that should come into your minds. And for just for instance, let's consider this circuit of half adder. Okay, so now imagine we have this circuit over here, which has an XOR gate and an AND gate over here, and there are two inputs and there are two outputs. So now at t is equal to 0, okay, you start giving the inputs to A and B both at the same time. Okay, now will you get this output instantly? The sum and the carry, will you get it instantly? By default, we might think that we get this instantly. That is theoretically possible, but in the practical life, it's not that way because it takes some time for this gate to process the input and then give out the output. That delay that uh, this gate takes for processing this inputs is called as the propagation delay. And why that delay happens or is generated is because these gates are made up of transistors. I think most of you would have uh, studied about transistors, at least in your first year's course or even in your college yet. So I think basics you all must be knowing of the transistors, so I won't delve into them. So for instance, this is the CMOS representation of the AND gate, while this is the CMOS representation of a XOR gate. CMOS is a type of transistor that we are using over here. There are different types of transistors like BJT, CMOS, FET, FinFET, and there are multiple types of that. So this is just to show you that why there is a propagation delay that comes into effect in the real circuits that are implemented. And each of these transistors, right, they have something called as known as the switching delay. That means if you apply an input over here, it will take some time for the transistor to show the effect over here. Okay, so that is called as switching delay. It's something like this. Okay, this is how the real inputs are. Okay, this is a signal. This is a voltage signal. This is 0 volts, and this you can consider as 5 volts. Okay, this is how the input will be. This is the rising edge. This is called as the rising edge. This is called as the falling edge. So this is the voltage signal that goes as input to this circuit. Okay, now it has entered this transistor. Okay, now for this output to change, okay, it will take some time. That time is called as the switching delay. That means these transistors, let's assume that they understand that okay, now the uh, input has changed from 0 volts to 5 volts at this point, because this is a threshold. This is let's say this is 2.5 volts. Now the transistor knows that voltage is above 2.5 volts is considered as a logic 1, and below that it is a logic 0. Okay, so now let's say the voltage has crossed this. Okay, now it knows that oh, now the input has changed from 0 to 1. So now it will start to act on this new input. Okay, now for that new input to show up at the output over here, okay, it will take some time. What this transistor, let us assume that it just inverts the value. That means if you are giving 0 volts, it will give you 5 volt as output, and if you give 5 volt as input, then 0 volts at output. So initially there was 0 volt as input, so that means the output was 5 volts. Okay, it was 5 volts over here, and now the transistor has processed the input of this 5 volts as the input, so the output will be 0. And then again here the input is further falling down, so that it might not consider, but assuming that we are only checking for the rising edges. Okay, so to keep it simple, what my main point is that this delay is there for each transistor. This is a fixed delay because it will take time for the transistor to understand this change in the input and then reflect on this output. Okay, in reality there will be one load over here, which is, sorry, it's not a resistor, it's a capacitance load. Okay, and the output that we see is the voltage across this capacitor. Let me just make it clear. So there is a capacitor over here, and when the input change from 0 to 5 volts, this capacitor, let's say that it starts dissipating. Initially the capacitor was at 5 volts, and now the capacitor starts dissipating the charge. So now from 5 volts it will go down to 0 volts. And as we have studied from capacitor basics in our early college days, there is a time constant called as RC. This transistor acts as the resistance, and this capacitor will start losing its charge through this path. Okay, I have gone into this detail so that you can understand why there is a propagation delay in every circuit. However simple it can be, there is always going to be a propagation delay. So depending on how many transistors are put into these circuits, okay, depending on that the propagation delay will vary. Okay, let's for example assume that the propagation delay for an XOR gate is 10 nanosecond, and for an AND gate is 5 nanosecond. So that means your carry will be generated first, and then after 5 more nanoseconds more, then your sum will be generated. So so you started giving your inputs at t is equal to 0. At t is equal to 5, you got the carry output, but you still have to wait till the sum output is also generated. So the worst case delay in this circuit becomes 10 nanosecond. Whichever path takes the maximum amount of delay, that is the worst case path. Okay, just remember this point. We have to always find the worst case or the worst case path in any circuit, and you have to adjust all the remaining timings accordingly. That means if this output goes into the input of another block, okay, and that block has some output, so we must know how much time will it take for this from this input to finally reach this output. Okay, in order to calculate that, we have to know the propagation delay of each circuit. Okay, now that is clear, and previously we had seen this full adder, okay, for a 4-bit full adder. So is there a way in which we can so if you'll see here, the inputs come over here, like A0, B0 come here, and then C0 goes out. So that means this next block has to wait for C0 to come in. Okay, even though we already have A1 and B1 ready, it has to wait for C0 to come in, only then this output will be valid. Similarly for this one, this has to wait for C1 to come, then only this S2 is valid. And the last one, it has to wait for C2 so that S3 is valid. So that means to this last overflow bit, this is the this will take the maximum amount to get generated. That is the worst case path in this circuit. This path. This is the worst case path. So imagine if this entire thing is encapsulated into one big block and you are using multiple of these blocks over here. Okay, this goes as the output from here and this goes into the input of the next block. So that means the next block has to wait for all these four adders to generate their carry out, and then only this will start to take in the work on the inputs. So imagine if you are using 16 of these blocks for a 64-bit addition. So just imagine how long it will take. So so let's see if we can generate this overflow bit faster so that the next block doesn't has to wait for so many operations to happen before this block can start running. Yeah. Let's try and see if we can figure that out. Okay, that's what I explained here. The final overflow bit would take the longest amount of time to generate because of this dependency of the carry in for the full adder. So in this case, this is the worst case path over here. So here we try to use the expression that I had mentioned in the last class for carry out. Okay. C carry out is equal to C in dot A XOR B plus A dot B. We'll try to uh, use this in some other form. Okay. So remember, this is the truth table for the full adder. You can always pen it out on your own. It should be fairly simple. There are 8 combinations for C in A, B. Okay, and accordingly we'll have the sum and the carry out as the outputs. Now if you observe this table carefully, okay, now consider these two cases of carry out. They are always 0 irrespective of what is the C in. Okay, here we are trying to find the dependency of the carry out on the C in. If we can resolve that dependency, then we can quickly find the value of this because of this dependency, right? This is what is causing this whole propagation delay to exceed. So if you are somehow able to get rid of this dependency, then we are good, right? In order to find the value for this. So that's what we are trying to do over here. So next combination, if you'll see, so for the combination of A and B being either 0, 1 over here and over here, these four combinations, C in is in the first combination, if you see, C in is 0. Okay, and for this combination of AB, the same C in comes out as C out. Right here also, if you'll see, for the same C in comes out as C out. For this combination of ABC, we see this is the result of carry out. So if you'll see, there is a relation over here that we can find. When A XOR B is 1, the carry out is same as carry in. That means the carry in is propagated out to the carry out signal. That is what is the important thing to be noted. C in gets propagated to C out. That is why we represent it as a PI. PI will stands for the processing of the ith bit of the full adder. That means if there are multiple full adders, as we had seen in the previous diagram, this is this represents I0, this represents I1, this represents I2, and so on. Okay, this is the full adder. A0 represents the first bit of the A number, and B0 represents the 0th bit of the 0th bit of the second number. So if you want to generalize this, this is how we represent it. This is a full adder, ith full adder, and the inputs are AI bi, and there is a ci. Okay, and there is a carry ci plus 1, because this ci plus 1 is same as c out over here. This will go into the carry in of the next block. So this becomes the carry in of the next block, right? If you consider this as I plus 1, so this becomes a ci plus 1. So that's how is the notation. Coming back to this truth table, so C in gets propagated to C out when A XOR B is 1, right? Here if you'll say 0 XOR 1, 1, 1 XOR 0, 1. So when this condition is satisfied, the C out is same as C in. Same over here, 0 XOR 1, 1, 1 XOR 0, 1. The carry out is same as C in. Now we are left out with the last two combinations over here. Okay, here if you'll see, irrespective of what is the value of C in, we get the C out as 1. That means the carry out is gets generated. There is no dependency on C in, but there is a dependency on AI and BI. Okay, over here if you'll see. So only when AI and BI are 1, that's when you get the C out as 1, right? So we say it as the carry out gets generated, because this is the case where A and B are both ones, right? So that's why we can represent this as GI. That means the carry out gets generated by the expression as AI dot BI, that is AI and BI. Okay, so now if we club these two conditions, what do we get, right? So pi dot ci, this comes from the first condition, plus gi. So that means we are just writing the expression, the same expression over here, right? Here if you'll see, this is gi, this is pi, and this anyway is ci, right? So the same thing we have written over here, but we have just generalized it for a ith full adder. So now if you see, we have just reduced the expression for carry out. Okay, we can immediately get rid of this C in because of this. We'll see how. Okay, if you'll see here, this is what is the circuit looks like. You don't have to get scared over here. It's very simple. Okay, Pi, if you'll see, the expression for Pi is A XOR B, A XOR B, and Gi, the expression is AI and Bi, so that is this. And the carry Ci plus 1 is basically this Pi and Ci plus Gi. So that is what we get as this one, right? So now if you'll see, let's try to do it for a 4-bit adder. Okay, so we'll start from the Ci plus 1. So that is C3 is equal to G3, this becomes G2 plus P2 into C2. Now what is C2? Is equal to G1 plus P1 C1. Now what is C1? Is G0 plus P0 C0, right? Now if you see, now G0 is nothing but A0 P0, right? And C0 or P0 is A0 XOR with B0 and C0. So this, if you will replace it over here and this one over here, we have directly found out the value of C4, right? So this is how we can find the value without having to wait for all these values to get propagated till the last. This is how we optimize the circuits. This is just one way of improving the speed of finding the C4. Okay. Always when you get a problem, right, we try to understand what is the problem first. Here the problem was you have to find this C4 as fast as possible. So what we did, the main bottleneck was this dependency that came over here. So what we try to do, we try to find ways to eliminate this dependency of C4 on this. And that's what we did over here, right? And how did we do that? We took help of the truth table. We tried to find relations between how this carry out is acting under certain conditions of inputs. And then we try to form a relation between them so that we can finally resolve this dependency. Okay. So this is how we try to generate this, called as a fast carry generation circuit, or it's also called as a carry look ahead or a CLA, because we are looking ahead in the carry. That means it's like looking ahead in the future. So that's why it's called as a carry look ahead or a fast carry generation circuit. And this is how it looks. Okay. So let's stop over here today, and we'll try to understand what are timing diagrams and what are hazards in the next class. Thank you.